In this lesson, we're going to introduce the first of the three types of precipitation reactions, or first of three types of aqueous reactions that we really want to focus on. This first one's called precipitation. In fact, this is one that is kind of like the basic ones that we tend to use, the more fundamental ones. And then everything else after this uses a lot of the principles we learn about precipitation reactions to then apply to the other types. In case you're wondering, like I said, this is the first of the three types of aqueous solutions. So the other two are going to be acid-base reactions and then also redox reactions, reduction and oxidation, or oxidation and reduction. Anyway, let's go ahead and take a look at precipitation reactions. So basically what happens here is that you're going to take two solutions of some chemical compounds, and then you're going to mix them together to form an insoluble product. An insoluble product, meaning it's not soluble, right? The solid is something that is going to then be created. So you look at this diagram, this little picture on the right, you have this solution right here that's just yellow. You had this solution originally, which was clear before you added it. And so by adding this yellow sort of solution to this mixture, it ended up kind of forming this sort of cloudy sort of thing that appears and it's starting to hang out. This is again known as the precipitate. This is the solid. And eventually it'll settle down. We also use language like, oh, the precipitate crashes out of solution, the precipitate, or something precipitates out of solution. And yeah, most of you are probably thinking, okay, isn't that like rain? Yeah, it's sort of similar where it sort of sinks and slowly falls from the top to the bottom. Now, this is going to be an example of a nice precipitation reaction, which gives you a nice color. We'll be using this specific reaction for a while. For this one, we'll have potassium chromate and barium nitrate. So those are yellow and colorless, respectively. All right, so potassium chromate, again, that is the solution that's there. The barium nitrate is that solution that was clear here. Right? Kind of imagine that this was all clear before you mix them. And again, just know that these are dissolved in that water, right? So these are not like pure. This solution here is not like a pure sample of potassium chromate. It's potassium chromate in water. By the way, the fact that this is also a yellow precipitate is kind of a coincidence that it matches the color up here. That's not something you want to read too much into. The point is, it forms an insoluble product. This is a product that's not dissolvable in water. And you see that in this equation right here, right? You have Kr blah blah, that's going to be aqueous. You have this, that's aqueous. But then on the product side, it forms a solid product. So it turns out this barium chromate is the precipitate, right? That is the thing that is crashing out of solution. To help us with this, we have to understand the solubility rules. The solubility rules is basically a summary of all ionic compounds and how soluble they are in water. If something is insoluble, what do you think the state of matter that will apply is? And it ends up being what? Insoluble is solid, right? That means it can't dissolve. Ionic compounds are solids at room temperature in any situation otherwise. So yeah, it's going to be a solid. If something is soluble, what state of matter do we use? We use the AQ one. All right, so it's kind of tricky. Remember, soluble does not apply to S. This is the coincidence there. You also have a solubility rules reference sheet. You might find it helpful to memorize it, but let me go ahead and point this out to know what you need to look at. Here we go, solubility rules. Now, this is a reference sheet again that you are going to use to help you do precipitation reactions. Notice that there are 6 rules, but of course these 6 rules have a lot of kind of parts to it, so let's go ahead and try them out. First of all, notice these first chunk right here, that refers to soluble substances. So if you see these in a watery environment, you typically can expect them to be dissolved. These substances, right, on the bottom, these 2 rules, these again apply to substances that when they're in watery environments, they typically do not separate or do not, dissolve into that water. So let's kind of look at some of the language and make sure that we know sort of how the pattern works. First of all, this one right here, all compounds containing alkali metal cations and the ammonium ion are soluble. So if you remember, alkali metals are your group 1 metals, so things like sodium and potassium. What they're saying is that if a substance has sodium and then something else afterwards, or potassium and something else afterwards, it's going to be soluble. Notice how I don't even care what the other part is, right? That's just sort of assume that if it's got those sodium something, potassium something, ammonium, right, NH4 something something something, those are going to be soluble, guaranteed. There's no need to second guess it. Number 2, all compounds containing nitrates, perchlorates, chlorates, and acetates are soluble. So in the same way, kind of looking at the other side, look at the anion side. If something contains nitrate, right? So NO3 is that. If it's something nitrate, soluble, done. Right? You don't have to even second guess it. Acetate, same thing, C2H3O2. If it's got something in front of it and then it follows up with acetate, guaranteed soluble. What about the next one here? All chlorides, bromides, and iodides, right? So we're talking about chloride ions, bromide ions and iodide ions. These are the ones, of course, I'm writing them as individual ions, but as a part of a compound, they might be like, NaCl, or they might be part of FeCl3 or something like that. If you see these, right, you can pretty much guarantee that it says here, all of these are typically soluble, right? So once you see that there's chloride in there, you can kind of disregard what the other part says, then know they're soluble. But this is the first time we'll see this, where it says except those that contain Ag+, Pb2+, or this business. So if I see NaCl, just kind of out of context, and I say, hey, is this soluble or not? Well, you know that it's got a chloride. Also, you know that it has a sodium, so you know it's going to be soluble. But if I was looking at the chloride side, right, I can check this list and say, okay, chlorides are soluble except those that contain Ag, that, and that. Well, this is not one that contains an Ag, a Pb, or an Hg. So I know this is going to be soluble, so I make it S. What about for our friend FeCl3? Well, if I'm looking at this initially, right, I don't see anything about Fe, so nothing here says anything about Fe, but I do know that my chlorides are generally soluble. Except, right, I have to double check this and know that Ag+, Pb2+, and Hg are not there. So we know it's soluble. Good enough. Or, wow, I just said the wrong thing. I just did exactly what I said not to do. I realized that's got to be aqueous, and that's got to be aqueous. There we go. All right, so we're all set there. And then you look at the last one right here, same thing. Sulfates are soluble except for those that contain yada, yada, yada. So once more, one of those exceptions you have to make sure you're careful of. So as you use this, read the whole line. Don't just kind of count on this first line saying, oh, soluble, done. There has to be some follow through to check that their exceptions don't apply. On the other hand, you have substances that are generally insoluble. So like this first one, number 5 right here, all hydroxides are insoluble. All right, so again, don't just stop there. There is an except compounds of the alkali metals and then a couple of other ions. So once again, if I see NaOH, right, this is the polyatomic hydroxide, I hope that I'm not careless enough and I'm like, okay, hydroxide, I know they're insoluble, and stop there, because then I'd forget. What do we learn about in the first step, or first rule there? It says that this was always soluble. So really, if anything containing sodium, right, these alkali metals, if you see it in solution, it's going to be aqueous, right? But more importantly, if it does have OH, and then you have some other ones like, I don't know, maybe FeOH3, right? Well, hydroxide is there. I recognize that Fe isn't any of the exceptions, right? It's not an alkali metal, it's not calcium, strontium, or barium. So this one in a watery environment will be solid. And then the same thing applies here. All compounds containing phosphate, sulfide, carbonate, sulfite ions are insoluble, except those, and yada, yada, yada. All right? So that's how these solubility rules work, and you always want to reference these as you do this. So as you look at these examples, you have a couple of opportunities here to try this out. So write the appropriate state of matter symbol when each substance below is in an aqueous environment, in a water environment. So like this first one, KCl, right? If I remember, K is an alkali metal, Cl is a chloride. So the easier one to use is just to say, okay, yeah, it's got an alkali metal, that's going to be aqueous. Don't even have to worry about the chloride part. What was this next one? FeNO3, my nitrate. The rule says in number 2 that nitrates are all soluble. So I don't even have to care about what iron is. I can know that it's going to be soluble right off the bat. Bromides are generally considered soluble, but then this is one of the ones that's got the exceptions. And then Ag, if you look at the list, let's do that right now. Ag, right, silver, all bromides are soluble except those that contain silver right there. So boom, then we go ahead and know this is going to be insoluble in water. So let's put this again kind of to a general set of rules. We can actually predict precipitation reactions because of these solubility rules. These tell us a lot of information. So generally speaking, you'll always be given 2 solutions of different ionic compounds. That's almost always how these start. This is a really good way to at least recognize that this is going to be a precipitation reaction. Step 2, identify the component ions and then go ahead and swap them out. Right. So your component ions can basically switch place to like positive with positive, or if you go negative, just make sure you swap them out so they make a new ionic compound so that your new substances are still a positive ion and a negative anion. The thing is though, at least one of the product needs to be insoluble. If it turns out when both products are soluble, then no reaction occurs. There's a little why here, and I'll let you kind of maybe talk through this one, think through this one on your own. But we'll talk about why sometimes if you have no soluble products, we just consider that to be a no reaction. Anyway, the point is, look for at least one of them to be insoluble. And then write out the equation with legitimate ionic compound formulas, right? So all those same rules that we did before, making sure that they're overall neutral, appropriate numbers of ions to represent that as overall neutral, using the parentheses, all that again is still saying the same. We're doing nothing new. And then finally, do the whole balancing and adding the states of matter. All right, let's go and try this out. We got a couple of examples here where it says, write the balanced chemical equation when solutions of each are combined. All right, now if you notice, these are all words, so once again, you have to do a little bit of translating. Sodium sulfate, Na2SO4. Now, we're assuming that it's in a solution form, so let's jot a little AQ there. And my other substance is lead nitrate. That's going to be PB. And you know what? Let's try another color here, and let's make it a little bit more fun. PbNO3, lead nitrate. Once again, it's also aqueous. Do notice that I also left a little bit of space here. I probably should have made that more obvious. I did leave a little bit of space here in case I do have to throw something in there to balance it. All right, so what do I get? Now, I'm going to go ahead and anticipate two products, right? Because I'm going to take one of these component ions, sodium or sulfate, and swap it with one of these two, lead or nitrate. All right, so lead's an ion, nitrate's an ion. We'll swap it with one of these two. For the sake of keeping it consistent, let's make sure that our sodium, let's kind of just say our sodium and our lead, we're going to trade places, right? So what's going to happen here as a result is that I'm going to have lead and sulfate over here, right, which was in red, sulfate together there. And I'm going to go ahead and write out my other proposed product, which is going to be Na, that's going to be in red, and my friend nitrate. Okay. Now, before I go any further, right, I have to make sure that this is a legitimate compound. And with legitimate compounds, right, lead is a +2 ion, sulfate's a -2 ion. So it works out that you only need one of each. This is actually fine the way it is. What about sodium and nitrate? Sodium is a +1 ion, nitrate's a -1 ion. So if you look, hey, check it out. These two are actually, again, going to be already balanced. So if you notice over here, right, there's NO3, 2. I'm not just going to blindly carry that over here just because I see it before, right? I'm not just carrying stuff over. I'm writing legitimate compounds using the nitrate ion. Same thing with sodium. I'm not just going to blindly carry the sodium over here and say Na2 immediately because, again, I have to write legitimate compounds. Now we go ahead and write some states of matter in here. Some of you may be looking ahead and knowing that this right here is actually going to end up being a solid, right? So if you look back at the original solubility rules, right? Sulfates are generally soluble, except those that contain, boom, lead, right? So we go ahead and make that solid. It's insoluble. And then the other one, sodium nitrate. Both of these we typically know are soluble, so aqueous there. And then finally, balancing it out, we go ahead and slap a 2 right in front, and then we are set. That's basically it. Now again, this happens when we know, or we can anticipate that one of these is going to be a solid. So that reaction does occur. What about the next one? Potassium nitrate and barium chloride. Here we go. So potassium nitrate, that's going to be KNO3, and barium chloride. All right, let's kind of keep this more consistent. And barium chloride. All right, so barium chloride, BaCl2. All right, so when you look at this, right, you have your component ions, and you're going to try and swap them. So I have my K here, my Ba here. I'm going to try and swap them into something new. So what I'm going to kind of anticipate is that we'll have a barium combining with a, oopsies, you have a blue barium combining with a nitrate, right? These two are going to come together at some point. And you're also going to have a potassium being combined with a chloride of some kind, right? Just generically writing those next to each other. I don't know how many of each it takes to combine them into a legitimate compound. Some of you might want to go ahead and do that, but I want to do this first. I'm going to see whether or not these form legitimate compounds, right? Or sorry, excuse me, if these are going to be soluble in water. So barium nitrate, well, barium I don't really know anything about, but what about our friend nitrate here? Well, as it turns out, nitrate is one of those very soluble substances. So if anything is with the nitrate, it's probably soluble. So I know this is going to be aqueous. In KCl, well, K, again, I recognize that as an alkali metal. And I don't, again, you kind of look at this if you want, but chloride generally are soluble as well. But as long as you get the alkali metal, you know this is aqueous. And if you remember from before, if both of these are aqueous, we're not going to have a reaction. So, frankly, you can at this point stop doing anything else. If I know I'm not going to form at least one insoluble product, and if I know I'm not going to form at least one solid, then I can go ahead and stop and just say no reaction. All right, you can abbreviate it as RXN, or if you really even can't even bear to write those extra 3 letters, you can just do NR for no reaction. I'll try the last one up, potassium hydroxide and iron 3 nitrate. All right, and then once you finish that, you can go ahead and try some more here. Same setup. You have sodium sulfate and calcium nitrate for the first practice problem, titanium 2-chlorate and sodium phosphate for this other one. And then finally here, this one's going to be kind of going backwards a little bit, where it says for the following precipitate, right? So you have 2 different problems here, but for these precipitates, suggest 2 aqueous ionic compound solutions that can undergo a precipitation reaction that will generate this precipitate, right? So you want to be able to make this as a solid in your precipitation reaction, but that does require 2 original ionic compounds that can be dissolved in water, that are both aqueous, that are both soluble. That will eventually precipitate this out. So you're going to have to do a little bit backwards thinking here and applying those solubility rules. All right, so once you do that, that'll do it.